So in this video we're going to derive the power reduction and half-angle identities for cosine, sine, and tangent. And the basic idea behind the power reduction identities is that we want to be able to take a cosine squared, a sine squared, or a tangent squared and have an identity that allows us to rewrite the squaring of those three trig functions without a squaring in it. So you see in each of these three identities, the cosine terms are linear or to the first power. And that's why this is a power reduction identity. These power reduction identities are particularly useful, for example, if you go on to take calculus and you have to do something called integration. These identities will help us to integrate squaring the squares of cosine, sine, or tangent functions, which would otherwise be difficult to integrate. The way that you come up with the power reduction identities is you start with two of the double angle identities. So in a previous video we established or derived the double angle identities for the cosine function, and you pick either of these two identities and you just simply solve it for sine squared or cosine squared. So we essentially take one identity and from it create another identity by rewriting one that we already know in a useful form. So for example, this one, we could add the 2 sine squared of theta to both sides, which would give us a cosine of twice theta, plus a 2 sine squared of theta, and it would be equal to 1. And then we could subtract the cosine of 2 theta from both sides, which would give us a 2 sine squared theta on the left and 1 minus a cosine of 2 theta on the right. And then we would just simply divide both sides by 2, isolating the sine squared and identifying a mechanism for rewriting the sine squared without a squaring in it. And we would go through the same process with this one. We would just solve for cosine squared to find a way to rewrite the cosine squared without the squaring in it. So I would start by adding 1 to both sides, which would give us a cosine of 2 theta, plus 1 equaling 2 cosine squared of theta, and then we would just simply divide both sides by 2, isolating the cosine squared. And by doing that, we have the power reduction identity for the cosine function, a way to rewrite cosine squared without a squaring in it. And then to come up with the identity for tangent, it's just simply a matter of understanding that the tangent is equal to sine over cosine, which means that the tangent squared of an angle is just going to equal the sine squared of the angle over the cosine squared of the angle by the ratio identity. And if we know what the sine squared is, which we do, we can replace sine squared with that identity, cosine of 2 theta over 2. And the cosine squared, we know what it looks like. It looks like a 1 plus the cosine of 2 theta all over 2. And the 2's are in the denominator position, so they're going to simplify to a 1. And we're just left with the ratio of the numerator to the ratio of the denominator, establishing the identity for the tangent squared. So the idea of constructing new identities from already established identities allows us now to come up with another identity. So we can derive the half-angle identities from the power reduction identities. And the way that we do it, what we do is we make a substitution. We let theta equal the twice alpha that we see here. Twice alpha is just some angle. Let's represent twice alpha with an angle theta. And if we do that, we can replace the twice alpha that we see here with a theta. We can replace the twice alpha in the power reduction identity with a theta. But dividing both sides by 2 also tells us that theta over 2 is equal to alpha, which means we can come in here where the alpha is and replace it with a theta over 2, and we can replace this alpha with a theta over 2. And then To get rid of the squaring on the sine and cosine function, we take the square root of both sides. So we say, hey, I'm going to take the square root of both sides, which is going to kill the squaring right here. So I'm going to wind up with a cosine of theta over 2 equaling, or I'm going to come up when I take the square root of both sides, square root will kill the squaring, will leave me with a sine of theta over 2. And we know that we're going to do the square root of both sides, so we're going to get a plus or minus the square root. And it's going to be plus or minus the square root of 1 plus cosine theta over 2, plus or minus square root of 1 minus cosine of theta all over 2. And then the way that you decide whether you use the positive square root or the negative square root, it depends on the quadrant in which theta over 2 lives. So if we're thinking about the unit circle, we know that the cosine is just the x-coordinate on the unit circle. So in quadrants 2 and 3, the x-coordinates are negative. So if pi over 2 is an angle that lives in quadrants 2 or 3, then we choose the negative square root. And if theta over 2 happens to be an angle that lives in quadrants 1 or 4, where the x-coordinates are positive, then we choose the positive square root. So it's quadrant driven, and it's going to be the same with the sine function as well. We think about the unit circle. We identify that the sine is the y-coordinate on the unit circle, so if theta over 2 is an angle that lives in quadrants 1 or 2, the y-coordinates will be positive. We would pick the positive square root, whereas if theta over 2 lives in quadrants 3 or 4, where the y-coordinates are negative, then we need to pick the negative square root. And the tangent function, you get to derive this identity as a homework exercise. How exciting is that?